Hi, I am Amir Araste, and in this video we will walk through the QuickStart notebook of Optiwindnet. We will go step by step to understand how the example works and how you can run it yourself. To get started, let's head to the Optiwindnet documentation page and read the docs. From the sidebar, we can navigate to the QuickStart section, where the QuickStart notebook is provided. QuickStart shows the minimum steps needed to run an electrical network optimization in a wind farm using Optiwindnet. You can also explore other notebooks here. We have two main series of examples. The first series is for network and router API. This is the high-level and user-friendly interface, and it is recommended for most users. If you are interested in finer control and advanced settings, you can also check the advanced API examples. On the QuickStart page, we have the option to run the example directly on online servers. However, in this tutorial, we will download the QuickStart notebook and run it locally. The link on the main documentation page takes us to the folder that contains all the example notebooks. In the repository, we have multiple notebooks. The notebooks that start with a letter are related to the high-level API. In this group of notebooks, the notebooks starting with A are generic examples. The notebooks starting with B illustrate specific routers, and the ones starting with C are for integration of Optiwindnet with other tools. Now let's download the QuickStart notebook and save it in a local folder. Now let's open the notebook and run it. In this tutorial we are using VS Code, but apparently you can use whatever you feel comfortable with. As stated, this notebook demonstrates the basic Optiwindnet workflow, from creating the network to running optimization and viewing the results. If the Python kernel for running the notebook is not selected automatically, we need to link it manually to the virtual environment that we created for this tutorial. In case you need help setting up your environment, please refer to our first tutorial, which is dedicated to installing Optiwindnet. Also, you may face this prompt to install a package for running the notebook if not already installed in the environment. This package is not an Optiwindnet dependency, but it is required for running the notebook files. As you can read here in this part of the notebook, a wind farm electrical network optimization using Optiwindnet involves two main components: a wind farm network, which contains the problem data, and a router, which describes the method used to solve the problem. The optimization can be performed using these steps. First, create a wind farm network instance, then define a router, then run the optimization and get the result. The wind farm network component we import from Optiwindnet in this cell stores the turbine layout, as was mentioned before. And after running optimization, it stores the optimized network as well. There is also some location data provided inside the Optiwindnet package. In this notebook, we are choosing one of the available locations. You can check the related notebook for more details about this. Now we can use the loaded data to instantiate the wind farm network object. The only additional information that we need is the cable data. The easiest way to define the cables is by providing a single number. Optiwindnet will interpret it as the maximum number of turbines that can be connected by the available cables. To make sure the wind farm network object is initialized correctly, we can plot the location. For more details about plotting, you can check the dedicated plotting notebook. Now that we have created the wind farm network, we can define a router and run the optimization. 3 built-in routers are available in Optiwindnet as shown in this table. EW router does not require any argument. HGS router requires a time limit, and MILP router requires the solver name, time limit, and gap value. Let's start with EW router, which is a heuristic router. As we can see, EW router is very fast and it is producing a design in milliseconds on my laptop, which has these specifications. One important note is that when we call optimize multiple times on the same wind farm network instance, the previously stored solution and related information such as the network graph, total cost, and total length will be overwritten. You can verify this by checking the updated total length or by plotting the optimized network and comparing it with the earlier results. Also, the important point about HGS router is that the main stopping criteria is the defined time limit. So choosing a good time limit is very important when using HGS router. To learn more about that, I recommend checking the notebook dedicated to HGS router to find out how to choose the time limit for HGS router wisely. Now if we compare the result, we can see that HGS router produces a better design compared to EW router. Also keep in mind that HGS router always produces a radial topology. In a radial topology, each turbine has at most 2 connections, which means a maximum degree of 2. In branch topology, there is no strict limit on the number of connections per turbine. Finally, let's design the electrical network using the MILP router. MILP router provides high quality solutions with guarantee, but it may take several minutes. Also note that if a wind farm network object already has a solution, MILP router will use it as a warm start. If you want to avoid warm starting, you can create a new wind farm network instance and run MILP directly on it. The procedure to use MILP router is same as the other routers. We pass it into the wind farm network and run optimization. We can see, for example, in the output log that the model is warm started because we already optimized the network with other routers. If you don't want to log outputs, you can simply set verbose to false when creating the MILP router. Finally, if we look at the solution info, we can see the defined values for MILP router arguments, as well as information about runtime, objective value, and the final relative gap. By comparing the total lengths, we can see that MILP router provides the best design, but with a longer running time. That finalizes our tutorial. If you found this useful, please support us by giving a star on our GitLab or GitHub repositories. And enjoy using Optiwindnet for optimizing wind farm electrical networks.